Welcome everyone. Today we are going to understand the entire mathematics behind linear regression. It is one of the easiest algorithms to understand, but there is a lot of mathematics that goes behind its understanding, like how it works, what is happening. It is easy once you get a hang of it, but before that, you need to understand and have a mathematical grasp over all the concepts that it has. So, yeah, linear regression time today. One of the easiest algorithms, but still a lot of maths to consider. Now, suppose you are predicting something, right? You have a data set which, let's say, you are doing house prices prediction. So, based on some features, you are trying to predict the price of a house. So, you have some, let's say, features like area of the house, number of bedrooms of the house, and then you have the price. So, based on this, you want to predict the final price of the house. So, let's say there is something called x, which is a two-dimensional vector, right? Now, suppose we are talking about x1 I. So in your data set, there will be samples, let's say I is equals to 0 all the way up to I is equals to n. And the number of features, so features are area and bedroom, so it can be daisy d1, d2, and something like this, right? So your data set can go from, let's say it has n rows. So it starts from I equals to 1, I equals to I equals to n. And you have features which are going from d1, d2, and up to some d dimension, right? So what does this represent? This represent the ith sample in your data. So you can pick any row in your data or any sample in your data, and x1 will represent the first feature of that particular training sample or instance. And what will x2i represent? In our case, x1i will be area of the ith house, and x2i will be the number of bedrooms of the ith house, right? And now we will define some sort of a function, let's say h of theta, sorry, h of x. It can be defined as theta 1, or sorry, theta 0 plus theta 1 times x1 plus theta 2 times x2, since we have only two features in our data set right now. But suppose if you have d features, it can be theta 0 plus theta I xi. It will go all the way from I is equals to 0 to I equals to d. So we have I equals to 0 to I equals to d, right? Now, why it is called a linear regression? So focus on the word linear. So this is a polynomial of linear manner, right? There are no terms like x square or x cube or x e to the power x. Anything like this is not there. All of the terms are linearly related to each other, and we are defining a function that takes x, which will be, let's say, your house, a feature vector of your house, that and for that you want to predict the prices, and it will have some theta as its properties, and we will multiply and add them together to get the final price. So just to write it again, x theta x will be theta 0, I goes from all the way up to d, theta I times xi. This will be your prediction function, right? Now these theta i's, which go all the way, let's say, to d. So there will be d theta, small thetas. So they can be theta 1, theta 2, all the way up to theta d. And there will be theta 0, which will be your bias. So it is same as the equation of a line, which is y equals to mx plus c or mx plus b. B can be considered as a constant or a bias in this case. We also add a bias. Uh, this can also be written as something like h theta x equals to theta 0 x 0 plus all the way up to d theta I xi. So these are your original features of a house, and we set x equals to 0 to 1. So we finally get h theta x as I is equals to 0 all the way to the d dimension. So I will start from 0 instead of 1, and we can directly write it as theta I times xi. I hope this is clear. Very easy to understand. So now we have our h function, which is this. It can also be written as theta t times x, right? So uh, let's take out the dimension. Since it is a regression problem and we are predicting a scalar quantity, so scalar would be in R. So this has to have dimension, let's say 1 by 1. So your theta can have dimensions. Theta will be a vector of theta 0 all the way up to theta d. So the dimension will be d times 1, and x is your row or a sample of your data, and it will also have d features. So it will start from, or d plus 1 features in this case. So d plus 1 are the theta and d plus 1 will be features. So the extra 1 is coming from the bias term theta 0 and x 0, which will be equals to 1. So x1, x2, and so on. So the dimension will be again d cross 1, but we want 1 by 1 dimensions for the h theta x. So if you calculate the dimensions after transpose, it will be 1 by d, and this is d by 1. So when you multiply them together, you get something of a dimension 1 by 1, right? So now you can simply write h of x as theta t times x. It is looking like alpha, so I'll write it again. Theta t times x, right? Now, our goal is to make this function such that whatever our prediction is, it is as close to the original value. So we already have prices in our data set. We want that based on a sample, whatever h function, this function, hypothesis function predicts, it should be as close to prices, right? The goal is to keep them very close. Now, to do that, we define something called a cost function. So the use of cost function is nothing. It will give us the idea of how far are we behind from the original prices. So in the case of linear regression, let's define a cost function j theta as half of I equals to 1 to the number of training samples h of theta xi minus yi the whole square. So this is some sort of a mean square error, right? You will see there is a division by 2. You will realize after we look at some other steps why 2 is there. It is just to ease our calculation steps, nothing else, while we are taking derivative of cost function to minimize it later on. Now this gives us the error. So this is our prediction. This is our original value, and we want prediction to be as close to as value as possible. Now this square term amplifies the error. So suppose your h theta x for a particular sample is 1, and y for that particular sample, which is the original value, is 2. So this term, the square term, will come out to be 1. But suppose h theta xi is 100 now, right? Now the error term will come out to be 98 square, which will be huge. So this design of cost function penalizes very far away errors. So if this is your prediction on a number line, and if this is your original value, if the difference is small, the cost of the penalty cost will be lower. But if it is much farther away from the original term, the difference will be huge and you will be penalized a lot. The model will be penalized a lot, right? Now, how do we get theta? Because in the end, if you realize, this term, we already know x. So how good our prediction function is, it always depends on the parameters, in this case theta. So our goal is to select theta such that we are as close to the original value. So there are various ways to do that. We will be looking at an iterative method right now called gradient descent. It is one of the most famous methods to solve or to update the parameters of a particular model, right? So it is defined as, let's say you have theta 0 all the way up to theta d. So for a particular theta, let's pick out one of them. It is defined as theta j minus alpha times differentiation of cost function, a partial differentiation of the cost function with respect to that particular weight. What is this equation and how do we make sense of it? Suppose this is a function fx and it is taking x on the x-axis, and we want to find out the value of x such that the value of fx is minimum. So we want to find x such that fx is minimum. One way that you must already know about is differentiation. So we can do something like this and it will already give us this value. We can solve for x here and it will give us this parameter. So this is the optimal value. Another way is to start at a random value of x. Let's say we set x is equals to some random value beta, right? Now we calculate f of beta and we see, and we are trying to optimize x such that f of x is minimum. So at this point we calculate the gradient. So we calculate gradient. Let's define a gradient function. So gradient of x will be equals to differentiation of fx by x, and at this particular position it comes out to be something that we don't care about right now. But if you look at this position here, you will see the gradient is positive. The slope of the gradient is positive. The slope of the function is positive, so the gradient is positive. So if we look at the update function, let's say the value of x here, since x is our parameter, so x will be updated, let's say learning rate, some sort of differentiation where in this case it is g of x and it is positive. So since this is positive, our learning rate is positive, we look at what is learning rate. uh, so which means for the next step x will be smaller. So suppose if at the initial stage it was 100 and gradient is 25, at the next step learning rate let's say is 1. So the next step it will be 75. It will be smaller than the previous x. Now we calculate, now we repeat those steps again. At this point again the slope is positive. So in the next step x will reduce by some amount based on the learning rate. So learning rate basically identifies the steps. So how big of the steps you take in each iteration. If your learning rate is small, x will update very slowly. If your learning rate is large, it will update very fast, right? Now suppose if you start at a value of x which is on the opposite side of the optimal value, at this position the gradient will be negative. Now x will be updated such that there will be a negative term here. So negative negative is positive. So the new value of x will be greater than the old value. So we are moving in this direction. So in any case, at any random value of x that you pick up, we will always move towards the optimal value of x, regardless of where we start. So if we are starting here, we will move in this direction. If we are starting here, we are going to move in this direction. So gradient descent is very useful in this case. Why is it useful? Suppose your function depends on very large matrix of x, like say n by n matrix of x, and it returns some scalar quantity, right? And n can be thousands of values, right? So let's say n by n comes out to be a million, 10 to the power 6. 10 to the power 6 is a million, right? Yes. Um, in that case, to find the optimal value of all the elements in X, you will have to differentiate it a million times. Whatever you want to do, it is very a computationally expensive procedure, right? So the gradient calculation of fx will be a computationally expensive procedure. Instead of that, you can just use gradient descent. So x will be updated as such that it will update in slow steps based on the learning rate. In any case, for this is a bad example that I have given, because anyways you will have to calculate the differentiation of x at a particular point. But the point is sometimes the functions are too complex to find out the derivative. It can be anything like e to the power x sin x plus cos x, log x, pi e to the power x, anything like this. Let's say this is the function, this is your model for, this is your h theta x or hx, and you want to optimize it. So your way could be, you can differentiate it, set to 0, and that will result in uh, a huge computationally expensive process. Also, if you're doing it by hand, another way is you can solve differentiation by using limits. So you can calculate it by f of x plus h minus f of x divided by h, and take a limit of it, and h tends to 0. So this is much easier process to calculate the gradient at a very single point in the function. You can use this formula, and this is also very easy to program. Instead of manually writing a equation in your code that can solve the gradient, instead of that you can take a function, vary the variable by a very little amount, and see the gradient, right? So let's move on. So the update rule was theta j equals to theta j minus alpha times partial differentiation of the loss function. If we write it, so theta j minus del by del theta j, our loss function was uh, half of, let's use only one training sample for now. So half of h theta x minus y uh, times whole square. Since we already defined a loss function, where is it? Here. This is for the entire training sample. We are just taking out only one of them, just for the ease of differentiation purposes. So alpha del by del theta j, it will look like 2 by 2 h theta x minus y. And what do we have here? We will have this thing, right? So 2 by 2 will cancel. So theta j will come out to be this minus alpha times h theta x minus y. And if you, sorry, there will be no square term here since we already removed it during differentiation. Now h theta x, as you know, it's what? Sum of from I is equals to 0 all the way to d theta I times xi minus y, right? So this will be theta j minus alpha h theta x minus y, and the term here, what will it be? It will be minus, uh sorry, not minus, it will be x of j. So let me show it again. So it will be theta 0 x 0, theta 1 x1, some theta j that we are trying to update xj all the way up to theta d xd, right? Since when we are differentiating this term with theta j, all of these terms will go away and only this will remain. And when we differentiate this with this, we will get xj. So the final update rule will be this thing. Let me write it down again on a new page. So the final update rule for a single weight that we took out from, so this belongs to a set of theta or a vector of theta which goes from theta 0 to theta d. So theta j, update rule for theta j will be equal to theta j minus alpha, um, let's say what? What was it? This one. So this was for a single training sample. We can also write it for like this for a single training sample. for ith training sample, the update rule is this. So this is also called the least mean square method of upgradation of the theta terms. Now, we have derived the gradient descent rule or the update rule when there was only a single training example. So there are multiple ways to modify this method when the training set has more than one example. So first thing you can do is run a for loop from 1 to n, and you apply this again and again. Sorry, not 1 to n, 1 to d for all theta, basically. And also for all the samples in the training data. So for all theta, you will do this, and all for training for all theta from 0 to d, and for all training samples, which would be 0 to n, let's say, or 1 to n, whatever you may consider. So theta j will be equal to theta j minus alpha I equals to 1 to n. It will be theta h theta of xi minus yi times xi and jth feature. So this is the update rule if you have multiple training samples in your data. Very easy to understand. We derived for only one sample, but what if you have multiple samples? You can just apply this, right? We can also group all the variables together, and finally you can write theta as a vector. So not theta j, remember there is no j here. So theta, which will be a vector of theta 1 all the way to the theta d, it will can be updated as theta minus alpha, going from the first training sample to the last one, calculating the error, h theta xi minus yi and times xi. So see, there is no j here because we are updating all the theta at once. So all the d parameters, all the theta going from 0 to d will be updated at once using this update rule. So very easy to understand equation. Now this is basically what we call gradient descent. Now another way to solve, so this was an iterative method. Another way to solve is using uh, the matrix derivatives. So suppose you define a big matrix of all the training samples in your data, like this. So x1 transpose all the way up to xn transpose. So initially there will be multiple, let's say, so each x, so x1 will be a vector of dimension what dimension? It can be d times one dimension. So all the features will be laid in a column vector. So there can be area, number of bedroom, number of bathrooms, garden, yes or no, etc. So all of this can be laid in this column vector, which will be of shape t comma 1. Uh, and the transpose of it will be 1 by d. And when you group n training samples together, the shape would be n times d. So here in each row, you will have a training sample. So if we pick up one row, you will have number of bedrooms, number of bathrooms, garden, yes or no, um, area, pool, etc. Whatever your features are. So the shape of design matrix X would be n times d, right? And then you define a matrix called Y, which will contain your original values. So y1, y2, all the way up to yn. So the shape of this matrix will be n by 1, right? Now let's define something called x theta minus y. So x is what? N by d, theta is d by 1, and y is n by 1. And when you multiply them together and subtract them, you will get a matrix that is of shape n by 1. So it can be written as x1 transpose theta all the way up to xn, uh, what is it? Xn transpose theta minus y1 all the way up to minus yn. Right. Oh, a random line. Now, so that x theta minus y vector can also be written as h of theta x1 minus y1 all the way up to h of theta xn minus yn. Right. Now, we know this property that x transpose for a vector, x is a vector in this case, x transpose x just gives us the magnitude basically, that you can say like this. So half times x theta minus y vector transpose uh, x theta minus y vector, it will give us the sum of squares of these values, since that are the original constituents of that vector. I is equals to 1 all the way to I to n, and h of theta xi minus yi times whole square. So basically we can represent our loss function. So this is our original loss function. We can represent it in the form of matrix multiplication. So writing it again, so our final loss function in the terms of matrix, it comes out to be half of x theta minus y vector transpose x theta minus y vector. Now we want to differentiate it and find it the optimal parameters. So we can differentiate, take a gradient of the matrix J. Uh, let's multiply the terms inside. So half, it will be x theta transpose x theta minus x theta transpose y vector minus y transpose x theta plus y transpose y. So there's a transpose here, right? And when we are differentiating with theta, taking a gradient with respect to theta, this term does not matter. So you can remove it. So it comes out to be half. Uh, you can basically write this thing as theta t times x transpose x theta. So basically the property that we are using, so let me write down the two properties here that will be useful to understand what we are doing here. So A transpose B is equals to B transpose A, and another is gradient of B transpose X is equals to B, and gradient of X transpose X transpose AX will be equal to 2AX. So these are the two properties that we need to remember. So where were we? Yeah. And okay, now this thing can be written as y vector transpose times x theta minus y transpose x theta again. And we can add these together and we will get 2 here. So we can write it again like this: theta t x dx theta minus 2, and we can rearrange the terms in here and write it as x transpose y transpose times theta based on a property above. Now the gradient of this will be 2ax. This is a in this case. So half 2, the final gradient of j theta will be equal to this half of 2 x transpose x theta minus what? The transpose of this term minus 2 x transpose y vector. This 2 will cancel. We will set this equal to 0. We will get x transpose x theta equals to x transpose y vector. So theta optimal will come out to be x transpose x inverse x transpose y vector. So instead of using gradient descent to find the optimal parameters, you can directly plug in this equation. So let's identify the dimensions of this vector. So your final update, theta, the optimal theta can come out to be, writing it again, x transpose x uh, minus 1, which is inverse, x transpose and y vector. So this is n by 1, x transpose dimension is d by n, and when we multiply them together, we will get something called in the dimension of d by 1, and that is what we need for theta, a matrix called dimension with the dimension of d by 1. So basically we have looked at gradient descent as well as the final using matrix differentiation, the rule, which is this one. So you have two methods to update your parameters for linear regression, gradient descent, and the least square revisited method using a design matrix called X and then directly getting the gradients and setting it to 0. Yeah, that's it regarding the mathematics of linear regression that